Hello, welcome to Introduction to Composites. Today is the third day of the ongoing week, which is the sixth week of this course. Over the last 2 days, we have been discussing how to predict the strength of a unidirectional composite when it is loaded in the direction of fibers. And what we have found is the fact that a composite can fail in two situations. If the volume fraction of the fibers is extremely small and below a certain minimum number, minimum volume fraction, then the breakage of the composite will start with that of the fiber, then load gets transferred to the matrix, and then after some additional load the composite is going to fail. However, if the composite fibers volume fraction is more than this particular minimum value, then the failure of the composite, of the fiber and of the matrix material will be at the same point of time, and in this case the expression for the strength of the composite is found through a different expression. We have also in the last class developed the relation for a critical volume fraction, and if the fiber volume fraction exceeds this particular critical number, then the strength of the composite is higher than the strength of the matrix material. So, with this information we will now proceed to do two examples, so that we learn a little bit more about the failure of unidirectional composites in tension loaded in the length of the fiber. So, the first example for a system which has not one but two different fibers. So, it has one single matrix and two different fibers. So, you have a composite and it is having a matrix material, and then there are two fibers. So, you have matrix, then fiber A and fiber B. And then we have, so this table will give you the properties of different materials, all these three constituents. So, first thing is density. So, density is 1.3, these are specific gravities 2.5 and 1.6, and then we are giving you the mass fraction, not volume fraction but mass fraction of each of the constituent. So, this is 35%, 45% and 20%, and the Young's modulus of these materials. So, we assume that all these are materials with linear stress strain curves. So, this is given in GPa. So, Young's modulus for matrix is 3.5 GPa, for fiber A is 70 GPa and fiber B is 6 GPa. And finally, the strength of the material, each of the materials, and this is given in MPa, is 0. Oh, excuse me. So, this is also given in GPa. So, this is 0.06, 1.4 and this is 0.45. So, with this information we have to find out three questions answered. So, but before that, this is a rectangular slab of composite and we are loading it in this direction. Fibers are like this, and this cross sectional area A is 10 cm square. Okay. So, this is additional information which is given. So, the first question is, So, as I keep on pulling it, at some point of time something will break. So, what is the maximum load when nothing breaks? This is the first thing, when nothing breaks. So, if I increase this load beyond this threshold, something will break, either the matrix or the fiber or fiber B. So, what is that maximum load? Second question which I have to answer is, so let us call it P1, we will call it P1. Second question is maximum load when entire composite breaks. So, this is called, we call it P ultimate. Okay. And the third thing is, we have to figure out which component fails first, then next, and so on and so forth. So, sequence of failure. So, that is another thing we have to figure out. So, to do this problem, first we have to compute the volume fraction for all these components. What we are given is mass fraction, and earlier we had developed an expression for volume fraction. So, we have to compute the volume fraction and we also compute the density of the system. So, rho c is, this is the expression we had developed earlier, is 1 over by rho m plus mfa by rho fa. So, fa is the mass fraction of fiber A and rho fa is density of fiber A, plus mfb by rho fb. So, this equals .35. So, this is in percent. So, 0.35 by density 1.3 plus 0.45 by its density 2.5 plus 0.2 by its density 1.6, and that works out to be 1.74. This density is required, that is why we are computing. So, now what is, now with this density we can calculate the volume fractions of each component, because we know the mass fractions, and with this thing we can compute the volume fractions. So, volume fraction of matrix is what? Is density of composite divided by density of matrix into its mass fraction. And if you, it will be worthwhile to develop this expression once you go back from this lecture. So, this is equal to 1.74, which is what we have calculated, divided by density of matrix 1.3 into mass fraction 0.35, and this works out to be 0.47. Likewise, VFA, volume fraction of the A fiber, is 0.31 and VFB is 0.22. So, now we have volume fractions of each component. So, now we look at failure sequence. So, for failure sequence we have to compute. So, what are we doing in the system? We are taking this composite which has two types of fibers A and B, and we are increasing the load on the rod. On the rod we are, so first we put 10 kilograms, 20 kilograms, 30 kilograms, so on and so forth, right. And as we are increasing the load, what is happening? The length of each of the components is also increasing, right, and the length of each component. So, the matrix gets elongated by some amount, the fiber gets fiber A, fiber B, and the elongation of each of these components for a given load is going to be the same, because this is what we had assumed when we were developing the relation for EL, right. So, to figure out which component fails first, we have to figure out the breaking strains of each of these components. Whichever component has the least breaking strain, it will fail first. So, breaking strains so, first we compute for matrix epsilon mu. What is its strength? Its strength is 0.06 GPa, and its Young's modulus is 3.5 GPa. So, that works out to be 1.71%. Breaking strength for A fiber is equal to 1.4 GPa divided by 70, and that is equal to 2.0%, and breaking strength for fiber B, you can do the same mathematics, is 7.5%. So, what that means? So, because it is a load controlled experiment, what do we mean by load control? We are applying external load. We are applying external load because it is a load controlled experiment. First thing which is going to, and everything is having the same strain, the first thing which will break is the matrix in this case. Now, when we were discussing in the last lecture and last several lectures, we said that matrix can take a very large amount of strain. It fails in the last. In this case, it just happens that we have chosen a very fancy matrix which has a very low breaking strain. Okay. This is not the case for regular matrices. It just happens that this particular matrix is a very special type of matrix. Maybe it is a ceramic matrix. Ceramics, okay. Most of polymer based matrices can take very large strains, but maybe it is a ceramic based matrix. So, ceramic matrices, even if you pull them a little bit, ceramic is like a crockery, if you pull it even a little bit, it will crack. Okay. So, these special types of matrices can take very small strain. So, that is why this special type of matrix will fail first, then at 2% strain fiber A is going to fail, and then at 7.5% strain fiber B is going to fail. So, the answer is, so what is the failure sequence? So, sequence of failure will be matrix, then A, and then B. Okay. So, that takes care of one question, which is the sequence of failure. Next, the question is, what is the load when nothing breaks, and just if we increase the load a little bit more than that, then something is going to break, right. So, what is going to fail first? We will have the failure of matrix, and that failure happens at 1.71%. So, we have to figure out at what is the load level in the system when the strain is 1.71% in the system. So, the next thing is load when nothing breaks. That is the next thing we are trying to figure out. So this is the second one. So if nothing is broken, then what do? We know that the relation in a composite, stress in a composite in the longitudinal direction is equal to sigma m Vm, and now this has two fibers. So what is it? Sigma F stress in fiber A times V fiber A, volume fraction of fiber A, plus stress in fiber B times volume fraction of fiber B. So and then, but we do not know these values. So we know the volume fraction of each of these fibers, but we do not know stress in each these components. So we can calculate that. What is sigma m? It is equal to Young's modulus of matrix times how much strain level? 1.71%. So 0.0171. Sigma Fa is equal to EFA into 0.0171 and sigma Fb is equal to EFB into 0.0171. And we already know the volume fractions of each of these components. The volume fraction of matrix is how much? We just calculated it, it is 0.47, for fiber A is 0.31 and for fiber B is 0.22. Okay. So with all these, and we already know EM's Young's modulus, so we can calculate all this. So what we get is 422 MPa. But what is the question? We have to calculate the load. Load is not same as stress. So how do we calculate load? Multiply by area. So P1, so this we had said there was P1. So P1 is what? P1 is 422 into 10 to the power of minus 6 or 10 to the power of 6 into area. So 10 centimeter square, and we have to do it in meter square. Okay. So this works out to be 422 kilonewtons. That is my stress. So if I keep on increasing the load till it reaches 422 kilonewton, nothing breaks, and if I increase it maybe 423, what will happen? Once the load exceeds P1, what will happen? The matrix is going to crack. Okay. So if P exceeds P1, matrix cracks first. It depends how. Okay. So once matrix has cracked, all the load which is borne by the matrix, it gets shifted to fiber A and fiber B. So once it cracks, all the load gets shifted to other the fibers, but I can still keep on pulling it further, right. The next thing which is going to break will be what? Fiber A is going to break, and that will break at 2%. So next, so let's find out next breakage point. Next break point. So at the next break point, stress in composite will be stress in matrix times volume fraction of matrix. This is the general relation, plus stress in fiber A times volume fraction of fiber A plus stress in fiber B times volume fraction of fiber B. But the matrix has already broken. If the matrix is broken, this thing will be 0. We cannot use this term. Okay. So, this will be 0 because matrix does not exist. Okay. It takes no load, and sigma f a. So, the next breaking will happen at 2%, right. At 2%, what will be the stress in sigma f a? E f a times 0.02, and stress in B will be E f b times 0.02. Okay. You do this and you compute that, and we already know the volume fractions of fiber A and fiber B. We already know volume fractions of fiber A and fiber B. So, they are not changing. So, once we do the computation, this comes out to be 460 MPa, 460 MPa, and P2 is what? P2 is 460 into 10 to the power of 6 into 10 area. So, this is 460 kilonewtons, 460 kilonewtons. So, the next breaking will happen at 460 kilonewtons. So, I have pulled it at 1.71% matrix breaks, I pull it further at 2% fiber A breaks. Then what happens? Once fiber breaks, its load also get transferred to fiber B, and fiber B will break only at what? 7%. So, let us see what happens. So, at load required to break fiber B, because this fails in the end at 7%. So, in that case, sigma C, again we will use the same formula, sigma m V m plus sigma F A V F A plus sigma F B V F B. Okay. But this is already 0. At 7% matrix is already broken, at 7% fiber A is also broken. So, the contribution from these two terms is going to be 0, and sigma F B will be what? E F B into 7%, and V F B is how much? 22%. So, you do this all this calculation and you find that this is only 99 newtons, 99 megapascals. What does that mean? That once the fiber A breaks, it transfers all the load to fiber B, but just to break fiber B you only needed 99 megapascals, right, and all this extra stress has gotten shifted to it. Fiber A is going to break at 460 megapascals. Okay, let's do one more computation. 460 no, one second. P3 is equal to 99 kilonewtons. Okay. So, once fiber B breaks, 460 kilonewtons is transferred to how much? To fiber B. I am sorry, once fiber A breaks, once fiber A breaks at breaking point, it is having 460 kilonewtons, right? All that load gets transferred to fiber B. Fiber B can only take 99 kilonewtons. Fiber B can only take 99 kilonewtons at 7% load, right, at 7%. So, fiber B cannot handle all this extra load which it gets. So, the point what I am trying to make is, once matrix breaks, it transfers the load to A and B, that load can be taken by fibers. But once fiber B breaks, then there is complete failure. So, you have 1.7% failure, more load, 2% failure, and then all of a sudden 7% also strain gets generated and everything fails. So, the question, the answer to this first question is, so what is the maximum load when nothing breaks? That was, we have calculated 422 kilonewtons, and maximum load when the entire composite breaks, that is 460 kilonewtons. So, the point what I am trying to make is that when we do analysis of cracks and failures in composites, it requires a little bit more thinking and to be more aware of the physical processes which are happening, and using that understanding we can predict failures of different components of the material. Tomorrow we will do one more example of failure, and that will be related to critical volume fractions of a fiber matrix system. But this discussion on failure of fiber matrix system today, I hope is helpful in making you understand the complexity involved in predicting failure of composite materials, and we will continue this discussion tomorrow. Till then, have a great day. Bye.